Hello, everyone.
Mm,
Slides are fine?
Yes,
Okay.
ma'am.
Yes,
Okay.
ma'am.
So we were at this position, the second interpretation of Lagrange multiplier in context of output maximization. Any question for this uh, another or the second interpretation? This is fine to all of you.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Very good. Before giving the interpretation for the Lagrange multiplier, I mentioned about solving equations 3 and 4. We get the optimum values of two inputs, and to check whether these optimum values are providing the output maximizing solution or not, we have to consider the bordered Hessian determinant. Since here we have two inputs, the most relevant bordered Hessian is this 3 by 3 matrix. The first H1 bar, we do not need to check because that follows the default sign. Therefore, we start with the second one. And the second one is given by this particular factor. Now, how we got this thing? Are you familiar with this idea? How we got minus
Yes,
R1? There
Yes,
is a
ma'am.
mistake. This
yes, ma'am.
minus
Yes,
R.
ma'am.
Yeah. Minus 0, minus R1, minus R2, minus R1, minus R2, F11, F12, F21, F22. So this minus R1 and minus R2, etc., how we got it, or 0, how we got the border,
Ma'am, Z
taking the
lambda lambda.
taking the
Z
derivative with
lambda 1,
respect
Z
to,
lambda 2.
yeah. So there was no lambda, there was mu this time, but you are
Huh.
absolutely right. Yeah. So we are considering our second order derivatives with respect to mu. So del square V by del mu square is giving the value 0. Otherwise, del square V by del mu del x1, which is exactly equal to del square V by del x1 del mu, that is minus R1. The other similar derivative is minus R2. So we are getting the border as del square V by del mu square giving 0, and other two values given by minus R1 by R2. So please check and rectify the typo. This should be minus R2. And this F11, F12, F21, and F22, this we are getting, taking derivative, del square V by del x1 square, del square V by del x2 square, del square V by del x1, del x2, del square V by del x2, del x1. And as you know, these cross derivatives you have to find for a single time, and then you will mention by Young's rule. So it is not required to take all the second order derivatives. So all 9 derivatives are not required. You have to consider the relevant derivatives, and then you can mention you are using the Young's rule. Okay. So for maximization, we need these bordered Hessian should alter in sign starting with negative. And what I mentioned, the first H1 bar is the default derivative. So that is always negative. Therefore, we start with this expression, and if this is positive, we claim that we are getting a maximum. However, if you have 3 inputs, you have to go one step further. So you have to consider this level, and you have to consider another matrix, another determinant in terms of all 3 inputs. So this is the position. So if you are comfortable with output maximization, next we will go for constraint cost minimization. Generally, we consider this context as the primal dual context. So if we consider output maximization is the primal problem, its corresponding dual problem is given by constraint cost minimization problem, where the cost equation, just a minute. Constant cost minimization, that is given by z is equal to r1x1 plus r2x2 plus b plus the Lagrange multiplier, and that is multiplied with the constraint q naught minus f of x1, x2. So here, I hope you are understanding, there is a single isoquant which is given by q naught is equal to f of x1, x2, and there is the cost, so subject to this particular level of output, we have a set of isocost lines. So we are expressing this particular function. If you understand this particular function, in the next step, you have to take derivative of z with respect to x1, x2, and then with respect to lambda. This will generate all first order conditions. Then you need to solve only for x1 and x2. So you will divide del z by del x1 by del z by del x2, which will give you f1 by f2 is equal to r1 by r2. The similar equation you got in case of the earlier context. And then you will solve this particular equation with this q naught minus f of x1, x2 equal to 0. And you will get the optimum values of the two inputs, x1 star, x2 star, in terms of r1, r2, and q naught. In the earlier context, you got the values in terms of r1, r2, and c naught. And here, you are getting the values in terms of r1, r2, and q naught. Next, interpretation of the Lagrange multiplier. From these expressions, we can write 1 by lambda is equal to f of f1 by r1 is equal to f2 by r2. And this is given by RTS, rate of technical substitution. This f1 by f2 is equal to r1 by r2. This is also called the rate of technical substitution is equal to r1 by r2, the input ratios. So it will be better if you write this expression first, and after that you write this one, and then you come to this particular context where 1 by lambda is equal to f1 by r1 is equal to f2 by r2. Now, if you get 1 by lambda is equal to f1 by r1 is equal to f2 by r2, this is quite similar to the earlier context, only here you are getting the reverse thing. In the earlier case, you got mu is equal to f1 by r1 is equal to f2 by r2. And here you are getting 1 by lambda, that is 1 by mu kind of thing, is equal to f1 by r1 is equal to f2 by r2. So since this is the dual problem with respect to the primal one, therefore you are getting the thing in terms of reverse position. The similar thing will happen if you consider the other context. In the earlier context, you got the Lagrange multiplier as dq by dc, and here you are getting it as to be dc by dq, change in cost due to change in output. So if you are quite comfortable with these positions, in the next step, we will go for bordered Hessian determinant, and we will show an equivalence between the bordered Hessian determinant of the cost minimization and the output maximization. So up to this, if you have any question.
So, ma'am, what will be the economic interpretation of 1 by lambda? So, is it the same as mu? So, and the economic interpretation of lambda will be the additional price of input if we change the output by 1 unit or something like that.
Here you will
So, how do we
write the
interpret?
reciprocal of the Lagrange multiplier is equivalent to the rupee worth of. The same thing you will write. You will just write reciprocal of the Lagrange multiplier. In place of
Okay, ma'am.
Lagrange multiplier, you will write
Hmm.
reciprocal of the Lagrange multiplier.
Okay, ma'am.
Rest
Okay,
of
ma'am.
the things are same. So here
Okay.
also we did the same thing. Reciprocal of the Lagrange multiplier is dq by dc.
Yes, ma'am.
Okay. Anything else regarding the first order conditions, regarding anything? So if this is fine, so we can consider the second order condition. Now here you are getting that the border has come in a different way, but this is the same thing. So we can add the border in this way, or we can add the border in this way too. The same thing. Okay, so first we can give f11, f22, f12, f21, these values, these four things, and then also we can put the border like this. So border may be to the left and top, and border may be to the right and bottom, same thing. So this is the bordered Hessian, and you know how we got this. Just we are taking the second derivatives of the entire thing, that is del squared z by del x1 square. So if we consider del squared z by del x1 square, what will be the value from this expression?
R1
Del squared z by
minus
del x1 square.
del x1.
There any
Oh, so
x1
that's
with r1?
minus lambda f11.
Minus lambda f11.
Very good.
Minus
So minus lambda f11. Okay. And then if we take the derivative with respect to x2, that is del square z by del x1 del x2, it will be minus lambda f12. Del square z by del x2 square, that will be
Minus lambda f2
Minus lambda
22.
f22.
And Young's rule, you
yeah.
will get the same expression, minus lambda f1 f2 or f2 f1, same thing. Del square z by del lambda square, 0, because there is no lambda here. But del
Hmm.
square z by del x1 del lambda, if you look from this position, del square z by del x1 del lambda, what will be the value?
minus f1
Minus f1. The other one will be minus f2.
minus f2.
So minus f1, minus f2, 0. Minus f1, minus f2, 0. Okay. Now you can substitute the values for minus f1 and minus f2 in terms of the input price and lambda, this expression, all these expressions. Okay. So minus f1 can be written as, from the first order condition also, you can say minus f1 is equal to r1 by lambda minus r1 by lambda. So if you substitute all these values, minus f1 and minus f2 in terms of minus r1 by lambda minus r2 by lambda, etc., we are getting these expressions. Finally, if we multiply this, or or if we multiply this by lambda square, actually what we are doing, then multiplying the third row by minus lambda square and third column by lambda, we are getting this expression. Actually, we are doing these things to get the similarity between the two exercises. Okay, so we are substituting this, multiplying the first two columns of the array by minus 1 by lambda, and then multiplying the third row by minus lambda square, and third column by lambda. We are getting this expression. And finally, we are coming to this. So please check these things. Please check these things. Just give me 2-3 minutes. There was a call, I will like to talk to the person for 2 minutes. So check all these things. And if you have any question, I'll give answer to this. Just give me 2 minutes. Hello?
Yes, ma'am.
Any question, anyone? Any problem? So this is fine to all of you? So output maximization, cost minimization, primal problem, dual problem, everything is fine to all of you?
Yes.
So if you are
Yes, ma'am.
okay with this thing, so this entire part of constant maximization, constant minimization, that is complete. Now we have to complete the short run, long run issues. So as I mentioned, the entire aspect we covered in context of output maximization and cost minimization, that is related to the long run, because we are considering all factors to be variable. So we have to consider a context when some factor should be constant, and the cost minimization exercise, etc., we will get, that will be the short run cost. Uh, 1 minute. Now, following this cost minimization procedure, when you are getting x1 star and x2 star and putting this in the cost equation r1 x1 plus r2 x2 plus b, you are getting r1 x1 star plus r2 x2 star plus b, which will be the, actually, if it is a long run cost, then there will be no b at all. The entire thing will be the variable cost. So it will be R1 X1 star plus R2 X2 star. That will be the long run cost. But if it is the short run context, you will get some fixed cost out of that. So the equation will be bit different. So that part we need to understand. And from there, we have to move towards envelope theorem. So there will be the slides for the next day where I'll discuss the difference between the short run and long run, and how the long run total cost curve is enveloping the short run total cost curves, and or long run average cost curve envelops the short run average cost curves. So all these things we will do. But before that, let me tell something about the numerical exercises. So this time too, I'll send you the problems from Henderson and Quant. In Henderson and Quant, there is a mixture between output maximization, cost minimization, profit maximization, etc. Therefore, you will get a mixed set. Okay, so chapter 4. So from chapter 4, you have to solve the exercises. So I think it will be better if I send the things and you start solving the things. And if there is any difficulties, so that we will discuss in the interaction class. Will that be better?
Yes,
yes,
ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
That will be better, because it's not that you will be not able to solve anything. And then we have to do something, a small part from chapter 5 too, because chapter 5 deals with homogeneous production functions, Euler's theorem and distribution. So this thing, and then short run, long run, envelope theorem, etc. So I think we need to do one more class in this sense. And after that, several, 1 or 2 classes based on solving this kind of thing. If you have some problems, that will be fine to all of you. I'll send you exercise of chapter 4, chapter 5, and chapter 6 too. Because in chapter 6, there are problems related to the markets already, market equilibrium. Already we did all these things. Different issues related to perfect competition, monopoly, oligopoly, etc. So I hope you will be able to solve these exercises too. And in this chapter, there is the cobweb problems too. And in your syllabus, you have the cobweb. So the relevant exercises, I'll send you and check. It may happen that all the exercises are not needed. I'll try to mention all these things. Okay, then it will be fine to all of you. So now you have to solve a number of exercises. That will be your task, to complete all these exercises so that you become comfortable with the position. After that, I like to start some assessments. So, if do you have any question? Otherwise, we can discuss some other issues.